guys, it's your favorite reliability test guy here with another fun-filled, action-packed video on reliability test and validation topics. This current video is an introduction to design failure mode and effects analysis. I hope you enjoyed this video, and if you do, don't forget to hit that like button and subscribe to my channel. Alright, let's get started. In this video, we will learn about DFMEAs and how to create one. Whether you call it a DFMEA or a DFMEA is fine in my opinion, and I've heard different companies adopt either one when discussing their risk assessment document. It all depends usually on who the original expert was that they hired who introduced DFMEAs or DFMEAs into a company's design process. In this video, we will cover definitions of DFMEAs, the contents of a DFMEA, and we will cover and go over a DFMEA example. Below is a high-level summary that demonstrates the process from requirements to end results and test reporting. In this video, we will cover the risk assessment portion of the process for failure mode identification, effect, and causes. So, what is a DFMEA? A DFMEA or DFMEA is the Design Failure Mode and Effects Analysis. It is a tool used to assess, capture, and form a plan on mitigating failure modes. As you go through and assess different parts and functions of your system and their failure modes, you will prioritize the failure modes such that some might not even be assessed due to the project schedule pressure or because the issue is so minute it is not even worth an investment of time. The failure mode could be a minuscule and be an unexpected reporting or flag status change on the back end of a software program, for example. That is not how it was intended to operate, but does not impact user function, and the user will never detect this back-end software glitch. Another example is customer nuisances, perhaps an app that occasionally crashes while a customer is using it, or a computer that crashes and restarts but fully recovers occasionally. These are considered soft failures, as they are recoverable, but can be an annoyance to your customer, especially if it ends up happening more frequently. Now we are getting into things that can really hurt your company or brand, hard failures, which result in costly warranty claims, product returns, and loss of brand equity. You can leave customers stranded in the case of a passenger vehicle breaking down, or a laptop that crashes and does not recover for a college student as he or she writes their final report that is due in the next few hours. These are failure modes that you want to prevent, best case, or reduce the frequency of to a minimum. Do not ignore these identified types of failure modes, or you will pay the price down the road. The last type of failure mode example is one that results in injury or loss of life. This is a all-hands-on-deck failure mode that requires multiple eyes and inputs to eliminate. You should invest a lot of time in testing and design improvements to prevent any safety-related failure modes, especially failure modes with a high number of occurrences or frequency. For example, you could have brakes that go out on a vehicle, or a battery-powered device going into thermal runaway and bursting into flames. These are failure modes you would obviously want to avoid with your product. Let's go ahead and define what a failure mode is. A failure mode is an event or an occurrence that you can physically see, hear, feel, or even smell in some instances. But this is not always the case, as in a minute glitch that happens on the back end of a software program like we discussed earlier, which a customer will never see. However, a software engineer may see it when reviewing data from a system or product's data log. Let's take a look at some failure mode examples. These are purely arbitrary examples that are failure modes that you may have experienced or read about in news articles or some variation of. Don't focus necessarily on the failure mode itself or my reasoning for the failure mode, cause and effect. However, pay attention to the relationship and meaning applied to each of these examples. Example number 1 is a smartphone that turns off unexpectedly when 10 apps are open and ran simultaneously. Example number 2 is a passenger vehicle that stalls when driven through 2 feet of water. Example number 3 is a heat shield on a spacecraft that fails during re-entry. Let's quickly define effect and go over some follow-up examples based on the failure mode examples. What is an effect? An effect is the result or byproduct of a failure mode that has an immediate impact on a function or operation of a product or system and can vary in severity from minuscule or none issues to a life-threatening event. Let's apply this effect definition to the failure mode examples we reviewed previously. In the case of a smartphone, having your phone powered down and not restart until an internal component of this phone cools down would be a very frustrating scenario for a customer to experience. In the case of a passenger vehicle that stalls when driven through 2 feet of water, this immobilizes the vehicle, strands the driver and any passengers, and can damage the engine or cause long-term degradation as a result of water entering the engine. In the case of the heat shield failure on a spacecraft during re-entry, this would result in a total loss of the vehicle as it burns up re-entering the Earth's atmosphere. You just lost human life in the case of a manned vehicle, or millions of dollars with the loss of a space vehicle itself. Let's go ahead and define what cause is. Cause is the driver or reason for a failure mode. A great example of this is in root cause analysis. The cause is the end result or the desired result of an investigation and analysis for a field or test failure. In the case of the smartphone, the cause was the result of a thermal design that was not sufficient enough for the amount of heat generated by the process, which causes the high temperature limit to activate and shut off the phone. A case like this could have been the result of an inexperienced thermal team, but more than likely was the result of a cost reduction either on the product company's side or on the supplier's side. In the case of a supplier, this is why it is critical to have your own quality team assessing the materials or components coming off the line from the supplier, as in some rare cases with lower tier suppliers, they may slightly reduce material thicknesses or cut corners to put more money in their own pockets, without realizing the implications that would result in the impact to overall system or product. This is a topic for another time, but I just wanted to address this. In the case of the passenger vehicle that stalls in 2 feet of water, it is time to take a look at that air intake to make sure that the location of the inlet to the filter box is not in a location that can easily pull in water, or you may need to add water or moisture resistance such as baffling or traps to prevent water from making its way into the engine. For you consumers out there, think twice about purchasing a cold air intake, especially if you're living in a location that gets significant rain, or you can end up damaging your engine and void your vehicle's warranty at the same time. A lose-lose situation for you. In the case of a heat shield, the materials used for shielding the intense heat that a space vehicle endures during re-entry can handle high air velocity and incredible high temperatures, but can be damaged fairly easily from mishandling. Make sure you have processes in place for handling, shipping, installation, and quality checks in place throughout the process to ensure a catastrophic event does not occur. Let's go ahead and learn about the content of a DFMEA or DFMEA, whatever floats your boat. Your company's DFMEA may slightly vary from this example, as each company may have their own adaptation for how they want to capture risk. However, the core content is universal, which we will cover. The upper portion of the DFMEA, or DFMEA, contains information about your component, subassembly, or the full system itself. The revision of the part, the team responsible for this particular DFMEA or DFMEA, the responsible engineer for the design and DFMEA, action completion, key dates, or required completion date to close out the DFMEA. The document number, which is whatever number and format you are using for your particular document control and management process. Who created the DFMEA, the date of the original DFMEA, and the date of any revisions to the DFMEA. Let's go through and define each column in the DFMEA table. The first column is the item and function. It describes an item of your component, subsystem, or system and its function that you want to analyze for a potential failure mode or failure modes. The second column is the potential failure mode. This is the perceived event that occurs when the item acts unexpectedly from its intended operational state. The third column is used to capture a potential effect or effects of a failure mode and can describe one or more effects that are a result of that particular failure mode. The fourth column is used to capture the severity of the effect or effects of the failure mode. Severity is a numerical value chosen in a scale between 1 to 10, with 1 being the least severe, with 10 being a life-threatening event when there is no warning signs during that occurrence. Let's take a look at a generic table that gives you an idea of how to rate your failure mode. This is a generic example, and your company may adopt some other types of definitions or designations for each of the values on the severity scale. However, this is a good example to help you understand what is meant by the severity values in a DFMEA. Keep in mind, filling out the severity and the following occurrences and detection are much easier for a product that is an update or an upgrade to an existing system or product that you have already field or historical data that allows you to have a good understanding of how the new system will behave. However, if this is a brand new technology or a new product for a newly discovered market, you will have to rely on educated guesses at a minimum, but an optimal strategy is to do some initial experiments or R&D testing and or a comparison of the risk of similar systems in use by your company or other companies to come up with your first pass severity, occurrence, and detection values. The next column is the potential cause or causes and mechanisms of failure. This is where you define one or more causes of the potential failure mode that you have identified. In the next column over, we will enter the number of occurrences that we are predicting for this failure mode. Again, this is a scale 1 to 10. Let's take a look at another generic table to get a better understanding of rating our occurrence value for a failure mode. As you can see, a 1 on the occurrence scale means the failure is statistically unlikely to occur. Depending on your effect and severity level, you may not even bother with any kind of physical testing for this failure mode line item. A 10 is bad news. Almost everything you ship out to customers is going to fail. Get ready for a warranty nightmare depending on the severity effect of the failure mode. And the next better up is the current detection controls column. This is where you enter your current means of detecting and preventing the failure mode in the customer's hands. For example, with a new technology, this is in the form of a design review to assess current design progress and initial testing performed. Care must be taken to make sure that the defect, depending on its severity, can be weeded out of the design or that it can be tested for with either physical testing or a combination of virtual and physical testing. Next up, determining your detection value. Again, it's a scale from 1 to 10. Let's take a look at an example table to give us a better understanding of how to rank our detection level. A detection level of 1 indicates that you are most likely and will find your potential cause and mechanism for failure with your design control. And a 10 means you're not going to find it and it's going to go undetected. And depending on the severity and number of occurrences, that's going to bite you really bad. So take a heavy look into your design control for a particular failure mode in your design. Alright, next up is the RPN. RPN stands for Risk Priority Number. It is the product of severity times occurrence times detection. RPN is heavily used industry standard for risk assessment in DFMEAs and can be used to determine sample size for your validation and reliability test plans. However, I'm not a big fan, and there are better methods out there, such as the Action Priority Ranking System. We will cover the pitfalls of RPN shortly, but for now, keep in mind that I believe RPN will become extinct in the future as it has its downsides, issues, and limitations. The next two columns capture the plan for mitigating the failure mode. The first column is the recommended actions. This is your plan for mitigating or reducing your severity, occurrence, and detection rankings. Oftentimes, severity cannot be reduced, as it is either the nature of the beast, as they say, as the failure mode is a catastrophic event, such as with a passenger aircraft plummeting to its demise. However, there is typically opportunity to reduce the number of occurrences and or detection through design and process improvements. You have heard or will hear, if you are new to engineering, the term RPN reductions. Typically, the RPN product is reduced by either reducing the occurrences or the detection or a combination of both. The second column is the responsibility and target date. This is the engineer who is responsible for driving the action or performing the action for the failure mode, and the target date to close out the failure mode item with satisfactory results that meet the company and customers' requirements. The last 5 columns capture the actual actions that were taken to reduce the failure mode risk or RPN reduction, the final severity, occurrence, detection, and of course, hopefully a reduced RPN value. Let's go ahead and create our very own DFMEA. I know you are all super excited and could not wait for this moment. No, me neither, but I recognize, and hopefully you recognize, the importance of DFMEAs as a tool and not just another I to dot and T to cross because your boss or company wants you to do it. A robust DFMEA is a lot of work on the front end, but can save you time and save your company from warranty costs, lawsuits, and a loss of brand equity in the long run for your product development and life cycle. So pay attention, put effort into your DFMEA, and follow through with the actions, and you will be a rock star in your company. In this example, we will analyze and create a DFMEA for the Blowhard Gas Company. We are developing a new propane tank for people to purchase when they buy our propane. Let's go ahead and fill out the upper portion for our part, the team, the part revision, subsystem, and so forth. All right, now that we've got the boring administrative mumbo-jumbo completed, let's get to the fun part. I'm going to be upfront with you here. The description I fill out here will be very short for time purposes, and you should invest more thought into the details for each of these columns. Also, there is no way you are only going to have 3 failure modes to identify, even for the simplest part. So don't just fill out 3 failure modes and then when your boss tells you you're an idiot, blame it on me. This is just a quick example to give you a general understanding of how to fill out a DFMEA without turning this into a 48-hour training video marathon. So keep that in mind. The typical DFMEA usually has a dozen or more failure modes for a super simple part, up to thousands of failure modes for a complex system. Let's fill out something for our item function field. In this case, we are analyzing the valve on our tank, which allows access to our tank to either fill or dispense propane gas. Next, let's fill out the potential failure mode that can occur during refilling of the tank. Next, the effect, which is not pretty when you overpressurize a tank. I would say the effect I predicted is pretty bad. So let's go ahead and enter a 10 there for our severity level, as this thing would probably blow without warning and badly injure or even kill someone, and you can destroy other items and parts of the building in the surrounding area. A potential cause is the tank getting overfilled. I'm sure there are other plausible causes and scenarios where this could happen that don't involve someone being an idiot, but most of the time it's because someone's an idiot. Let's go ahead and enter a number of occurrences. Well, recalling our example occurrence table, I think it's fair to say that 1 out of every 400 people is an idiot. So let's go ahead and enter a 5 for our number of occurrences. Alright, next is design control. Right now, I'm going to pretend we have none. No design reviews, no experiments or R&D, nothing. So I will enter a 10 for fun in my detection ranking. Alright, we are ready to calculate our RPN. Recall that RPN is the product of severity times occurrence times detection. Let's go ahead and calculate the RPN using the values we entered in the table. Now let's solve, and we get 500. So our RPN value for this example is 500. I want to pause for a minute to go back to a claim I made in the previous slide that RPN has its pitfalls. Let's go over a quick example. Let's say we have a failure mode that has a severity of 1, an occurrence of 10, and a detection of 10. Let's go ahead and plug these values into our RPN equation. Let's go ahead and solve. And this gives us an RPN of 100. Okay, cool. Well, hold on a second. Let's say we have a severity of 10, and an occurrence of 10, and a detection of 1. Let's go ahead and plug these values into our RPN. And look, we also get 100 once again. With the first example of severity of 1, I could give a flying flip about the other two rankings, as the severity ranking is the only thing that I pay attention to when prioritizing actions to take for failure modes. Honestly, with a severity of 1, even with an occurrence and detection of 10, this failure mode would end up at the bottom of my bucket of priority action items, as it is a failure mode that will not impact the customer, let alone the customer will never even know that it occurred. This is why prioritizing actions to work on first and determining test sample sizes for your validation and reliability tests based on RPN values is fallacious and potentially dangerous, as you may miss critical failure modes with a high frequency of occurrence, since RPN does not discern or weight severity, occurrence, and detection independently. This can be dangerous if you set a minimum threshold for high, medium, or low priorities for each failure mode using the RPN, as you could end up overlooking or waiting until late in the design game to verify and validate a potentially catastrophic failure mode. Okay, getting off my soapbox, let's get back on topic here. Let's go ahead and plug our RPN value into the table. If you're using Excel and you are lazy like me, do yourself a favor and create a formula for your RPN column to auto-calculate your RPN value based on your severity, occurrences, and detection. Work smarter, not harder. Alrighty, let's go ahead and create our plan for tackling this failure mode. We want to go ahead and add a overfill protection device, or OPD, and test to see if we mitigate this failure mode. Good old John Doe is the poor soul responsible for driving this failure mode mitigation plan to completion. And of course, management wants this done yesterday, so where are the results, John? What are you waiting for? We are setting up the DFMEA for this exercise, so we will not fill out the results section in this video, as John is still over there slacking off and not taking action fast enough to fix this failure mode that was due yesterday. Sheesh, what a slacker. Before I finish boring you to death, let's go over 2 more examples. Another tank valve operation failure mode is what we're going to cover. In this failure mode, the tank can explode or burn while filling or while in use. The effect is pretty bad. Injury, death, burning down your house, or a local convenience store where you're filling up your tank, and so forth. I'll go ahead and give this a 10, as this effect is going to be really bad and without any warning. Boom! Potential causes. Let's see, because people are idiots and do stupid stuff, like burn a cancer stick while working with open combustibles. Of course, there needs to be a leak too, but with a combination of a stupid person and a gas leak, it's a recipe for disaster. Again, I'm going to assume that 1 in 400 people are idiots and also don't know how to properly tighten a fit-in or use worn-out fit-ins and hoses that leak due to years of material aging and breakdown. So let's go ahead and put in a 5 for our number of occurrences. Okay, let's go ahead and look at our design control, which in this case, we're going to pretend we have a test to detect flames creeping into a tank resulting in an explosion. What a cool job that would be on the production line, am I right? In this case, we can detect the failure mode every time, so we are going to go ahead and enter a 1. Let's go ahead and enter our RPM value. Calculate it yourself and double check to see if I can do basic arithmetic if you would like. Alright, let's go ahead and enter our recommended action. In this case, we're going to use a check valve to prevent the flame from moving into the cylinder and going boom! We are still going to have a pretty sweet flamethrower, but at least the tank doesn't explode, right? Well, that's why we're going to go ahead and perform a verification test for good measure to make sure that the check valve operates as intended. And once again, that slacker John Doe is responsible for this one, and he should have gotten it done yesterday per upper management. Let's do one more before you fall asleep here. Again, with the tank valve. In the failure mode, the valve can break off when directly impacted. And the effect, well, once again, it's pretty bad. You know what happens when you release the end of an open balloon, right? Well, imagine this happening with a steel rocket. Yeah, it can be bad. I've heard urban legends of nitrogen cylinders tipping over and flying through concrete walls. Imagine what that amount of force would do to you if you got tagged by a pressurized cylinder on a rampage. I'm going to go ahead and put in a 10 here. I think that's a fair assessment. Okay, now on to cause. People are clumsy idiots and drop stuff that should not be dropped, so I'm going to go ahead and use my logic from the previous examples and put in a 5. Okay, on to design controls. We have a design review in place to review design progress and initial testing for this failure mode. So detection is pretty good, and we will go ahead and enter a 2 in this case. Let's go ahead and solve for our RPN, which comes out to 100. That number at this point should make you shudder based on the explanation I gave on the pitfalls of using RPN. For the recommended action, we will make a design change to add a shroud or protective barrier that will prevent the valve from getting impacted when the tank is dropped directly onto the valve. And we will test to verify that our design solution works. Notice in the photo at the bottom right hand corner, the brilliance that went into the years of development and refinement of the propane tank we take advantage of for our summer barbecues today. You can see that it has a permanently welded shroud that even has handles so you can carry it. Brilliant, world-changing innovation right there. Last but not least, John, what is the status on this action? Upper management said it had to be done yesterday. Alright, that's it. You can wake up now. We're done. My approach and some of the descriptions are comical. However, this gives you a good intro and start to creating a DFMEA for your product. Sorry I didn't do something more complex or high-tech, but I wanted to do something simple to give you a practical understanding on DFMEA development. Still confused or need help in developing your company's DFMEA? Reach out to me in one of the links below in the description to see how I can help or provide training services. Let's go ahead and discuss the key takeaways from this video. Take the DFMEA development process seriously, or you can suffer warranty and or safety issues later on when the customers are using your product. The DFMEA is a critical design and development tool. Don't go into developing a DFMEA with the mindset it is an inconvenience that your company or your boss is making you do, because there's a reason. Use the risks you identify in your DFMEA to help you design a better product. The initial DFMEA should be created early on in your development cycle. Don't wait until your boss asks for your DFMEA to scramble and throw something together to keep him or her happy. Start thinking about it and jotting down your risks early on so that you have a head start in developing your product design. I'm feeling really generous today, so here's a bonus tip. Take a top-down approach to the DFMEA process. Start with creating an initial high-level DFMEA for your system that can drive actions and design inputs and trickle down into DFMEA inputs for your subsystem and component DFMEAs. I'm in a really good mood today, so here's another bonus tip. Don't work in a silo on your DFMEA. You should be communicating and working with others in your engineering group or cross-functionally to ensure that you have identified and accurately documented all failure modes and their impacts for your design, and failure modes that may impact other teams' designs as well. Hopefully you have a systems engineering team and or a reliability engineering team driving these cross-functional DFMEA activities. But if not, be proactive, don't be lazy, and you will look like a star when you produce an awesome, robust product design. The DFMEA, along with a corresponding reliability and validation test plan and strategy, will ensure you minimize warranty costs and maintain and even build brand equity for your company. If you need help on your reliability and validation test plans or your DFMEA, or would like to get training, feel free to reach out to me at one of the links below. Hey guys, thank you for watching this video. If you have any questions, comments, or need any help with the reliability test and validation, feel free to reach out to me at one of the links below. Thank you for watching and have a great day.